So the subject is switching theory and logic design. We are going to study, and the same subject will be followed by your computer architecture in the fourth semester, microprocessor in fifth semester, and so on. So we'll study the basics of the digital logics. We'll start here. So anybody have you idea about the gates or something like this? Have you studied this? Okay, we start with the introduction, switching theory and logic design. Now first, let us discuss what the digital system is. So in the current scenario, whatever is present in the electronics, everything runs on the digital architecture, digital system. Now why we must understand the digital system? So we will take a quick look on into this. Digital systems are now used in communication, traffic control, medical treatment, weather monitoring, and internet, and so many things you are seeing around you is the digital system. When we talk about the characteristics of the digital system, the ability to manipulate discrete elements of information, we have 10 decimal digits, 0 to 9, 26 letters, alphabets, and 0, 1, that is the binary codes. The general example of this particular digital system is your digital computer. So what you are using, or your mobile phone, whatever it is, your pager, these all are digital. Now further, a digital system is an interconnect of digital modules which form the basic chapter of this course, that is the logic design. Now, after learning logic design, you can understand how a digital system operates in each basic logic module. So in this particular course, we are going to study the basic modules like your adder, your subtractor, how to construct a multiplier, how to store the memory, how to design a random access memory, how to RAM, SRAM, DRAM. All these will be discussed in this upcoming lectures. Now, objective with this paper is the objective of the paper is to felicitate the students with the knowledge of logic system and circuits, thereby enabling the students to obtain the platform to study digital system and computer architecture. Now, the both subjects are coming in your upcoming semesters. Now, outline of the course, what we are going to study throughout this semester. The first is number system, number codes, switching theory, combination logics, then integrated circuits, your ICs, sequential logic circuits where we store the memories, data like memories, counters, shift registers. Then we have synchronous sequential circuits, finite state machines where you can design a small digital system or of your desired characteristics, algorithmic state machines, fault detection and locations. These are the topics which are going to cover in the upcoming lectures throughout this whole semester. Now the text, as far as the textbook is concerned, for the last unit, there is a 4 unit, you will refer Joey Kohavi, switching theory and finite automata theory. And for the rest of the units, you have to follow Morris Mano, digital logic and computer design. Further, you can follow whatever book is available with you. And I think my lecture notes will be sufficient for you for this particular course. Now some other textbooks you can refer, that is RPGen, digital modern digital electronics. You can refer Anand Kumar, Fundamental of Digital Logics, Top Schilling, Digital Integrated Circuit. But as far as my opinion is concerned, if you are going to purchase the book, then it is Morris Mano, Digital Logic and Computer Design. That will be sufficient. Now let's start with the number system. What the number system is. From the starting of your school age, you are well known or well aware about the digital system. Decimal number. We have 10 numbers, 0 to 9. And suppose, let us take an example of the decimal number system. What we have a number 7, 3, 2, 9. here in the subscript, I have written the base, that is the decimal number which represent we have 10 numbers. That is called base. Throughout up till now, you haven't seen any system, any number system where the base is required. But when we are going to study digital system or switching theory, then it is always necessary to write the base as a subscript so that it can be well known to the reader or well known to the person that that which number system you are using, because 7329 is the number in decimal. If I write 7329 and the base is hexadecimal, then this will be totally different. Now let us take an example. Let us go through how the number is represented. 7 multiplied by 10 raised to power 3. 10 is the base. 3 is the position, that is the position 7000. Now 3 is represented 3 into 10 raised to power 2, that is 300. 2 into 10 raised to power 1, that is 20. 9 into 10 raised to power 0, that is 9. Now any number system will be represented in such a way, then this particular number, when we solve this particular equation, we will get 7329. In this way we represent the any number in any number system base. Now the digital computer represents a quality equal to 7000 plus 300 plus 9 tens plus sorry 2 tens here written wrongly written is 2 tens plus 9 units. Now we talk about the term radix or the base. Here in the decimal number, base is 10, means we are using 10 units which will range from 0 to 9. Now the coefficients here 7, 3, 2, 9, 9, 2, these are the coefficients. Now, a general form of number system can be represented with a positive radix r by a string of digits. Means in any number system we have to define the radix or the base, and it is represented by r. Now like this, we have, this is the decimal point. Here the coefficients are positive. Here the coefficients are negative. So I will write A0, A1, A2. These are the position. When we A0, the value this particular A0 will be A multiplied by base to the power 0. Now when I have to find out the value of A1, then A1 will be A1 coefficient A1 multiplied by 10 raised to power 1 up to like this. And here in the right hand side of the decimal point, it will be A minus 1, that is the coefficient, multiplied by 10 raised to power minus 1. For A minus 2, it will be A minus coefficients of A minus 2 multiplied by 10 raised to power minus 2, like this. Now here the AI is from 0 to R, which is the R is the radix, and dot is the radix point. The string of the digits represents the power series. Now we can represent it like this: number equals to summation I equals to 0 to n minus 1 AI into R to the power I. Here that is the left hand side, and plus the right hand side of the decimal, that will be j to the power minus m to the power minus 1 summation aj into r to the power j. Here the coefficients will be negative. So that's why I have taken the limit from minus m to minus 1. Now this is your integer part and this is your fraction part. In such a way, for any number system of base r or radix r, if we represent number in such a way, then we can say the number will be converted directly to the basic value, which is in the decimal number. Now here are the general representation of a decimal number or any base r. If here r is the radix, that is a base in general, so digits will be from 0 to r minus 1. If I take an example of decimal number, then the base is 10, then we can say that the digits will be 0 to 9. In case of binary, here the base is 2, so digits will be 0 to 2 minus 1, that is 1, 0 to 1. Now if I have some examples, now the power, if we say these are the radix powers 0, 1, 2, 3, 4, 5, then minus 1, minus 2, minus 3, minus 4, minus 5. So here will be r to the power 0. In decimal it is 1. In binary it is also 1. If the power is 1, then r to the power 1. For decimal, 10 raised to power 1 is 10. 2 raised to power 1 is 2. If the power is 2, then in case of decimal 10 raised power 2, that is the 100th position. And in case of binary it will be 4, 2 raised power 2 is 4, like this. Now in case of minus 1, if the power is minus or radix is minus 1, then the decimal value 10 raised power minus 1 equals to 0.1. And in case of binary it will be 10 2 raised power minus 1, that is 0.5, in such a way. Now again, take the same example, 7, 3, 2, 9. It is 7 into 10 raised power 3. Here the coefficient, this is A3, A2, A1 and A0. So I write this 7 into A to the power, R to the power 3. R is 10 in the decimal. 3 into base to the power 2. 2 into base to the power 1. 9 into base to the power 0, like this. Suppose I have a number system which has a base 5. So here the base 5 number, the range of the digits will be 0 to 4. 0, 1, 2, 3, 4. The 5 will never appear in the base 5. As 10 never appears in decimal number. It is 0 to 9. So I have a number 4021.2 base 5. So if I have to convert this particular number into the decimal number, or I have to find out its exact value in the decimal, then I will write here the coefficients is 0, 1, 2, 3. The 4 has a coefficient A4, this is A0, A1, A2, A3. So I expand this particular number 4 into 10 raised power 5. So sorry, 5 raised to the power 3. So 5 is the base, plus 0 into 5 raised to power 2, plus 2 into 5 raised to power 1, plus 1 into 5 raised to power 0. Here is A minus 1, plus 2 into 5 raised to power minus 1. And then this number comes to be 511.4 in base 10. But the value of this particular base 5 was 4021. We cannot read it like 4021.2. No, it will be 4021.2 base 5, and it is equivalent to 511.4 in base 10, like this. Now take an example of the binary number. I have a number one, I write this position is called LSB, least significant bit, and the leftmost part is MSB, most significant bit. So in binary number, we always read number from the MSB. So the number will be 110101. That is A0, A1, A2, A3, A4, A5, like this. So maximum coefficient is 5. So I expand this particular number 1 into 2 raised power 5. Here it is. Then 1 into 2 raised power 4 plus 0 into 2 raised power 3 plus 1 into 2 raised power 2 plus 0 into 2 raised power 1 plus 1 into 2 raised power 1. When I expand it, 2 raised power 32 plus 16, this term is 0, plus 4, this term again is 0, plus 2, 1. Then that number comes to be 53. Now the number is 53 in base 10. If the base is not 10, I will read it like 53 with base. Now again take an example of hexadecimal. I'll discuss it later on what the hexadecimal number. For this particular example, the hexadecimal number is of base 16. So maximum number will be 0 to 15, but 0 to 9. Then A is represented by 10 is represented by A, 11B, 12C, 13D, 14E, and 15 is represented by capital F. So air number is B65F base 16. So when I expand it, B stands for 11. So 11 into base to the power 3, A0, A1, A2, A3. 11, that is the coefficient, multiplied by base to the power position 3, plus 6 into base to the power 2, plus 5 into base to the power 1, plus F stands for 15. 15 into base to the power 6, like this. So when I will calculate this value, this number will be converted into the decimal number. So we can say that when we expand any number by its coefficient and radix to the power position, then that particular number can be directly converted into the decimal number. Now we take another example, some more examples. Here we have 4310 base 5, then it will be equals to 580. I'll expand in the same way, 4 into base to the power position, and the position is counted from the here decimal point 0, 1, 2, 3. The position of the fourth is 3. So 4 into 5 to the power 3 plus 3 into 5 to the power 2 plus 1 into 5 to the power 1 here, this last term 0 into 5 to the power 0 equals to 0. Then when I expand it, it comes to be 580 base 10. Another example, let us say that we have a number system of base 12. So 198 is not the value in base 10, 12. It is 198 base 12, and I can expand it like 1 into base to the power 2 plus 9 into base to the power 1 plus 8 into base to the power 0. When I expand it, this value comes to be 260. Now, when the base is 10, we can directly write what you are studying in the mathematics, that is this value is 260. But in case of base, any base other than 10, it will be 198 base 12. So let us take another example. Suppose 735 base 8, that is the octal number. In the octal number, when base is 8, then the maximum value of the digit will be 0 to 7. So 735 base 8 will be 7 into base to the power 2. So here we count the position 0, 1, 2. So 7 into base to the power 2 plus 3 into base to the power 1 plus 5 into base to the power 0. And it comes to be 477. That is 477 in base 10. Now binary special units, when we k, so 1k equals to 2 raised to the power 10, that is 1024. Mega, when you talk about the storage, the mega MB, megabyte. So here 2 raised to the power 10, 20 is mega, that is equivalent to 1048576. That is the value of the mega. Then giga is 2 raised to the power 30, that is 1073741824, that is denoted by capital G. Tera, nowadays the memory of your computer hard drive is terabyte TB. So 1T is 2 raised to the power 40. Now a 512 byte RAM. So 512 MB जिसको बोलते हैं, that is the RAM or size of the RAM. 512 MB memory is actually 512 multiplied by 1 M. M is equals to 2 raised to the power 20. This storage is in your 512 memory byte. Byte is 8 bit. 1 byte is equals to 8 bit. Bit in case of in decimal number we say digit 0 to 9, and in case of binary we say it bit. Single 0 and 1, there are 2 bits. So now we have when we have to convert the from numbers from one number system to another number system. So initially you are very much aware about the digital decimal number. So decimal number can be converted into hexadecimal, and hexadecimal back to decimal, decimal to binary, binary to decimal, decimal to octal, octal to decimal, decimal to any base r, or any from any base r to back to decimal. So when a number is in any base r, when we expand it by multiplying its position and the coefficients, any number system can be converted back into the decimal number. When we expand the number with multiplied by its base and the position, then any number will be converted to the decimal. Now again, the interesting what we are going to do in the digital system, there the conversion between binary to octal, octal to binary, and binary to hexadecimal, hexadecimal to binary. Now keep in mind that one question in your exam will always be there for the number system conversion. You have to convert from one base to the another base. So that is very much tricky and very much interesting topic which we are going to discuss. Now from when we have to convert from any base r to decimal, so what you have to do, you just have to expand the number, multiply by its base and the position. Now when we have to convert decimal number into any base number r, so what's the problem? Suppose we have decimal number n of base 10, and we have to convert it into base we have to find out the coefficient which has a base r. Base r may be for binary it may be 2, for octal number it may be 8, for hexadecimal it may be 16. So here the algorithm I am going to discuss is in a generalized form. It may be possible that you will find that it is a tough algorithm, but when we solve some examples, then it will be very easy. Now suppose we have a number n in base 10, and we have to find out the coefficients a0 to an if the number is integer. And when we so it will be like this: an to the an r to the power n plus an minus 1 r to the power n minus 1 and a up to a0 r to the power 0. This is the basic number which we have to find out. So this process can be done by the division process. Suppose what we do, we first divide number n with base r and find its residual. So whatever is the residual, that is kept aside. The first residual will be a naught, that is the first coefficient, this one a naught. Again here the quotient will be q1. Again what we do, we again divide q1 by r and find the residual a1 and q2, and this process continues until when we find out the final coefficient. Now take an example. Suppose we have to convert decimal number 41 into binary number. So here the first thing is we have to convert decimal number 41 into binary. So the base of the binary will be 2. So we have to convert 41 base 10 into any number base 2. So here r will be 2. So what we do in the division process, we have to first divide 41 by 2, and this process continues till the end. We have the residual 0. Now we have integer coefficient, remainder, and the coefficients. So 41 divided by 2, quotient is 20, remainder is 1. So 1 is the first coefficient. Now when we divide 20 by 2, the quotient will be 10 and the remainder will be 0. This 0 will be a1. Again I divide 10 by 2. This 10 is again divided. Quotient is 5, remainder is 0. We do this until the quotient is 0. Then 5 divided by 2, quotient 2, remainder 1. Now a3 is 1. Again 2 divided by 2, quotient is 1, remainder 0. Then 1 is divided by 2, quotient is 0, remainder is 0. Now here our quotient is 0. Now we have find out all the coefficients a0, a1, a2, a3, a4, a5. This a0 is your LSB, least significant bit, and a5 is your MSB, that is the most significant bit, and we'll arrange this number. Now 41 base 10 will be here, where I write 1 0 1 0 0 1 base 2. In this manner we can convert any number, any decimal number into any base number. Now this is the convenient algorithm process what we have done. Let us take some more examples. Now convert from decimal 153 to octal. I suppose that all of you please do this particular question in your book, and you can type the answers in your chat box. So it will be better to do practice and likewise. And this process will continue whenever I am going to take lecture. Please be seated with your register and pen so that you can solve out the questions. Now we have to, in this particular example, we have to convert decimal 153 to octal. The octal number base is 8. So what we do, we divide 153 by 8 and we arrange the quotient and the remainder. Remainder is your a0. Here the required base is 8. First 153 is divided by 8 to give in an integer quotient of 19 and the remainder 1. Then 19 is divided by 8 to give an integer quotient of 2 and the remainder of 3. Finally 2 is divided by 8 with a coefficient 0 and a remainder of 2, and the process can be conventionally manipulated as follows. Here we are dividing continuously by 8. Now the coefficient is, this first remainder is a0, a1, a2. Now I can write it like 2, 3, 1 base 8. And that means 153 base 10 is equivalent to 231 base 8. So I think we should stop our class here, and I suppose all of you please do some questions or some numericals based on the number system converters, so that it can be helpful for the next upcoming classes.